Hello? Am I working okay? Can you hear me at all? All right. Great. So I'm Michael. I work at Cray on this Chappell project. And the first thing I have to tell you is that you shouldn't take anything in this talk as a reason to buy or sell stock or do anything like that. Okay, great. Now let's talk about LLVM and Clang and Chappell. So here's a little bit of an outline. I'm going to introduce Chappell, because I would wager probably most of you have not heard of it or seen it very much if you've heard of it at all. And then I'm going to talk about how C interoperability works with Chappell. And then I'm going to talk about how we implemented a combined code generator that's like Chappell generating LLVMIR alongside Clang. And then we're going to talk about communication optimization, which I think is really cool and probably strange. Okay, let's go. So what's Chappell? It's a productive parallel programming language. It's meant to be, well, I'll get to that there in a minute. It is portable, it's open source, it's a collaborative effort. We have lots of contributors. It's sort of got a center of mass at Cray though. Its goals are to support general parallel programming, any parallel algorithm on any parallel hardware. That's a goal. I can't say we've achieved that. It's sort of impossible, but you know, we try. And we intend to make parallel programming at scale much more productive than it is now. So that's what we're trying to do. So productivity is a little bit of a hard term, right? Like, what does it mean to you? What does it mean to anybody, right? It could, well, for a recent graduate, maybe it means I want it to be something kind of like what I learned in school, right? I learned on MATLAB, I learned how to do physics or astronomy or whatever. For a seasoned HPC programmer, that's all that sugary stuff they don't need. They were born to suffer. What they really mean is that they want full control over the machine in order to ensure performance, because that's sort of their job, right? Their job is to get every ounce of performance out of their hardware that they can. And then there's computational scientists, maybe an astronomer or a physicist or somebody like that. They just want to express their parallel computations without having to wrestle too much with the architecture. So what we're trying to do in the Chappell team is make something that lets the computational scientists express what they want without taking away the control that the HPC programmers need, and do it in a way that's attractive to recent graduates from schools who are used to something like MATLAB or Java or Python. I'm literally pausing so you can take a photo. Okay, so the next thing I'll do is I'm going to go through a little example. This is the most trivial computation. Well, I think this is about as trivial as it gets. I guess Hello World is simpler. But Hello World wouldn't be a parallel program, then we wouldn't learn anything about parallelism, right? So anyway, this is stream. Stream just takes two vectors, adds them together while multiplying the second one by a scalar. So alpha is, you know, some value that's a scalar, and then other than that, we're multiplying two arrays and storing the result in A. So say we want to do this in parallel. If we're doing this in parallel, then on a shared memory machine, we'll want each core to have a chunk of each array, and they'll do their little part of the addition and multiplication, right? Okay, that's cool. And then we only need one alpha, right? Because why bother making copies of alpha if it's all on a shared memory machine? But well, if you were going to do it in distributed memory, like you've got a whole bunch of nodes in a cluster or something, those all have separate memories, and now, well, you need a separate alpha because you don't want to copy it every time you're doing a multiplication. So it looks slightly different. And then if you're doing both at the same time, well, now you've kind of got this nested parallelism thing. So that's even a little weirder. Okay, so how do people write this kind of thing now? Well, to do the distributed memory computation now, you'd use something like MPI typically, and most of this is just sort of boilerplate stuff, arguably, that MPI programs just have. This stuff is about, like, you know, loading up the problem so this can be a real benchmark. And over here is the actual code that's doing the, you know, vector addition and multiplication. So like the actual content is really those two lines, and there's just a lot of other stuff that you had to type in order to get your program to work. Okay, well, what if you wanted it also to work across a bunch of cores? Well, then maybe you would add some OpenMP, You throw some pragmas in here, and then you've got your OpenMP parallel 4, and now you can do that. Okay. And then now, everyone wants to do GPU programming, so what's it look like on a GPU? It's kind of the same kind of thing, right? Where you've got a whole bunch of stuff that you just have to deal with in order to make your program go, but philosophically, right, your algorithm is right there. Like, that's the real content. You've got 2 lines and then like 900 lines of scaffolding. Okay, so we think, on our team, we think that there are just too many ways of writing these things. And why are there so many ways? It's because all of these languages came from hardware, right? They said, well, what hardware do we have? How can we access whatever the hardware is giving us? Let's find a way to do that. So that's why you have these things. So obviously, since there are too many, we need another one. So here's what this program looks like in Chappell. There's just, I can't really see that well over there. Sorry. So when it says, oh, I know what I'll do. I'll walk. Okay. So right here, this declares some arrays. Those are just like the vectors in the problem. And then we initialize them. Those promote those values to the arrays. So that like sets all the slots in array B to 2. And then here, this is a promoted expression. So A, B, and C are arrays. Alpha is a scalar, and it does it element-wise by arrays. And then the only other thing to know here is that this dmapped and ... is the part that would make this work in distributed memory the way that I showed you a minute ago. So this same code, depending on what you put in that dmapped part, could actually implement all of these little pictures about what would happen. It could be totally serial, it could be parallel within a node, it could be distributed, or it could be distributed and across tasks or threads or cores or whatever you want to think about in a node. And I already said that part sort of describes how to do that. So we think that by carefully constructing the language, we can make it so that people can write programs this way, and the idea is that you can separate out most of the work of the algorithm from the work of specifying how will I make it go on this particular machine. Okay, so that was about Chappell. Now I'm going to go a little bit more towards LLVM. I'm just going to tell you a little bit about history of Chappell and LLVM at the same time. So one thing that you'll need to understand in order for this talk to make any sense is that Chappell started out a little bit before LLVM was released, as you can see in my little timeline. And as a result, we started out not using LLVM, right? Because it didn't really exist yet. So for a long time, we've been generating C code and then using the C compiler as sort of our back end, right? But recently, we're trying to get to a spot where we can use LLVM in a regular way. Okay. Other things on this chart that deserve a little bit of explanation. I have to walk over here so I can see what I'm pointing at. There's this LLVM just activates generate LLVM IR. LLVM wide opt is the communication optimization I'm going to talk about in a little while. This extern C code is a C interoperability feature I'm going to talk about. And then I think the rest of it should make sense to you. So as I said, we kind of grew up generating C code, and we're working on moving more towards LLVM, but that's important to know. So what's our compiler sort of flow look like when we're generating C? Well, we start out with a bunch of Chappell files that have some code in them, and we run the Chappell compiler, we make some C files, and then we run the C compiler, and we link in the Chappell runtime that would be a library, and also available to that C compiler, there's a bunch of header files that are in the runtime. So we got used to doing some things with this model that might be a little strange if we were starting from a pure LLVM spot. So how did we add LLVM support to fit in the same model? Well, here's sort of a picture, and I'm going to explain all of these parts individually, at least to some degree. So what we did is we made the front end integrate a little bit with Clang, so it can use Clang in order to work with header files and these extern blocks for C interoperability. those work together to produce a combined LLVM module. We run some LLVM optimizations, and then at link time, we link in that C runtime that I was talking about before. But you'll notice that actually the processing of the header files, like if we had static inline functions or something like that, that happens from Clang, and so those things will end up in our LLVM IR module. Okay, next I'm going to talk about C interoperability. So since Chappell's a new language, it's not like, OpenMP plus C or something. It's really important that we have a pretty good interoperability story, because just telling everyone to start rewriting everything from scratch isn't really a good strategy. So hopefully that's obvious, right? We strive to support good interoperability with C in particular, and we think that it's important to be able to use an existing C library, and existing C libraries might have functions, variables, types, and macros, and you might need to be able to use any or all of those things depending on your library. The other thing is that when you're calling these C functions, it needs to be efficient, right? We're talking about a parallel language. If we made everything a lot slower, you wouldn't want to use our language even if you could make it parallel, right? So here's an example of C interoperability. So on the top, there's it's supposed to be a C file called add1.h, and it just declares a little function that adds 1 to its argument and returns it. And then there's a Chappell file below, and that just has this extern proc declaration right here. And that just tells the Chappell compiler what function is available from C that it should basically allow to type check and know is going to be there when it goes to sort of build everything together. And on the bottom, I just printed out the result of adding 1 to 4, and so you get 5 on the bottom here. I need to take a sip of water so you can meditate for a second. Okay, so what we did with extern blocks is that instead of having to write all of these extern proc declarations, there are other kinds of extern declarations you'd have to write for a real library. Instead of having to write all of those, you just put extern curly brace and then type in some C, and then our compiler knows that that's some C, and it will go and basically use Clang to parse it. And then down below, after you have done that, you can use the types, functions, and variables from that block as if you had declared them with those extern procs. So that's pretty cool, because now you could take some big library, like one of our users did this with the GNU scientific library. He just put #include GSL and then started using it, and he was pretty happy. So how does that work? Well, in our front end, we have a whole bunch of passes, but sometime after parsing, we have a pass called read extern C, and that takes some extern block declaration like here. It will pull out the contents of it and pass it to the Clang parser, that produces some Clang AST. Then we use that Clang AST with our own code to produce these extern declarations, just like you see down here. So it's actually a fairly simple use of Clang in the scheme of things. Okay, so next I'm going to talk about sort of what I call combined code generation, and it starts to get a little weirder, I think, now. So as I was hinting before, we'd really like to be able to inline C functions in our generated code. So why would we want to do that? Well, some C functions are just meant to be inline. Like we have some in our runtime where if we don't inline them, we see performance slowdowns. And our runtime is written in C. Well, you could say, well, why don't you just write your runtime in Chappell? Well, we could, but parts of the runtime aren't written by us. They're like, for example, QThreads, which is a C library, right? It's written in C. Somebody else wrote it. Part of the idea of libraries is you get to use other people's software. So, but we also use some third-party libraries like GMP, right? And so we can't say, oh, just rewrite all of GMP in Chappell. That kind of misses the point. Anyway, so somebody who's writing GMP, they're going to know what things make sense to inline. So it's important for us to be able to kind of honor whatever they were thinking about. But besides all of that, since Chappell kind of grew up generating C, it became normal to assume that we could do things like inline functions, because in the generating C case, that's not that weird. Or, for that matter, that C types are available, which is a little weirder, or that fields and C structs are available, or even that C macros are available. And those are sort of, I'd consider those increasing difficulty as we get to generating LLVM IR. So here's an example of a program. I tried to make something plausible to show you why you might want to access a field in a C struct, right? So I don't know if you've done socket programming before, but it's typical to make these little structures that have this sock adder storage thing and then a length so that you know how big your address thing was. And so this isn't even that crazy. But anyway, over here I just declared it extern record, or you could pound include in an extern block, right? And then the point here is down here, I might have some code that wants to directly manipulate that field, x.lang. So how do we do this kind of stuff? Well, when we are code generating, we sort of start out with a Clang code generator. It creates the module. We ask it to code generate for our sort of runtime headers, and we leave it all open. And then we will call these functions like get adder of global if we see a function we need to call, or convert type for memory if we see a type we need to be able to generate into LLVM IR, or this new function, get LLVM field number, if we have a C struct and we need to be able to get a field out of it. So get field number will let us generate a get element pointer type instruction for those. So and then there's little stars here. So this used to be something we needed to do with Clang internal headers, but as of Clang 5, we could do the top two, and then thanks to helps from reviewers, I was able to add this last one to trunk, so it should be in Clang 6, and then we won't need any special internal header kind of stuff for Clang to do this thing. Okay, so then the last thing is C macros. So here's an example that's sort of based on something that actually happens. It's usually a little more complicated though. So I might have some header file that defines a constant that's just like how many microseconds are in a second. And then I might have some code that uses that constant, right? How are we going to do that, right? If I'm trying to generate LLVM IR, I can't say, hey, LLVM, give me the IR value for this macro. It doesn't know about macros. Macros are a C thing. And likewise, I can't ask Clang to generate LLVM IR for a macro because, well, it doesn't even do that, right? All of the Clang code generator starts after it's pre-processed. So how could we possibly do that? Well, the answer is I don't really know. But I have some ideas, but what we actually have done for now is we have sort of a pattern matcher where we just go through all of the macros in the extern blocks and things that we parsed, and we look for some patterns that we know how to deal with, such as it's just a number, or it's just a number cast to a known type, or it's just two numbers added together, something like that. And that actually covers a lot of the common cases in C. There's sort of a pattern of using pound defines for these numbers. But something like a macro that's sort of pretending to be a function, I don't really have a good strategy for that. And I'd like to do better, but it will involve sort of more exotic ways of integrating with Clang, where we have to like maybe add functions at the end of the parsing while we're going and things like that that are even crazier. Okay, so the next thing I want to talk about is still in sort of code generation area, but it's about vectorization. And so I'm going to start out by talking about this idea of a for all in Chappell. So in the earlier example, when we were talking about stream, we had this A equals B times B plus alpha times C. That actually gets translated into this kind of loop that's a for all loop. And it's for all, and then it's zippering together these arrays, and then it has this simple body where everything is just one element at a time. So in Chappell, a for all loop represents a kind of a data parallel loop. If you're writing for all as a user, you're asserting that every iteration could be run in serial order, or they could all be run in separate tasks, and you're asserting you don't care what order they run in. Typically, the for all is implemented by dividing the iterations among a bunch of tasks, but the parallelism is actually controlled by whatever you're iterating over. So it's actually implemented in the module code, or possibly the user's code, how that for all statement is going to divide up the work. So to kind of illustrate a little bit, I have an even simpler example. There's sort of on the left, there's like users code that has a for all in my iter, and then on the right, there's maybe a library that's defining this parallel iterator. The parallel iterator has in it a co-for-all. Co-for-all in Chappell means create one task per iteration. So that's what's creating the tasks to divide up the work. And then inside the co-for-all, there's a loop doing whatever work happens inside of the task. So this is where we typically do that kind of dividing up we saw in that stream example. So the Chappell compiler uses a strategy of what we'd call iterator inlining to combine these things to the case on the bottom, right, where there's the co-for-all and then the inner for and then the body. Then after that, we'll turn the co-for-all into a loop that's basically creates a count of how many tasks it's going to make, and then it goes creating tasks to run for each element for each iteration in the co-for-all. And then it'll wait for all those tasks to complete. So that's sort of what it looks like for us. And right now we do all of this with outlined task functions because there's not really another way right now. So that's where I think a parallel IR could come in and fit pretty nicely with what we're doing. I think we'd need to keep some of the stuff about how the for all works, because we have this idea that the way the tasks the way the tasks divide up the work is implemented in user code, right? So we can't really just say, oh yeah, that's LLVM's problem now. But we could certainly benefit from sharing optimizations and representation about these tasks. Okay, so vectorizing. We'd really like to vectorize for all loops, and philosophically it ought to work because the for all loops, the sort of rule of it is that the iterations can run in any order, including all at once. And we've been thinking a little bit about vectorization. There's really sort of two basic strategies we could use, right? We could vectorize pretty early in the Chappell front end, where we just generate vector IR instructions. But that has some drawbacks, like, well, we don't get to benefit from the great work other people are doing in the LLVM community on vectorization. And if we're not very smart about cost modeling, we might start making things slower than they would if we didn't vectorize in some cases. Or we can use the LLVM loop vectorizer. There we generate loops with parallel loop access. The challenges then are user-defined reductions it's harder to see how we can indicate to LLVM passes that the loop is still parallel when we have a user-defined reduction. And we have some proposed language changes that might involve sort of moving a little bit of the programming model closer to GPU programming. And in GPU programming, you normally have this idea of, I'm going to query what thread number I am, right? So if you wanted to do the corresponding thing in vector code, you'd ask, what vector lane am I? And I don't even know how we would do that. So I feel like I sort of already said this, but I'll just go on. Here's a little bit of a summary of a possibility about how we could maybe encode user-defined reductions in a way that would allow the loop to still be parallel. I've talked to a couple different of you about this, and I think reactions I get range from you're crazy, why do you care, to, oh yeah, sure. But anyway, in here, the thing I'm thinking about is maybe we make an opaque function and indicate that it's associative and commutative. And then the optimizations might be able to know that they can reorder the calls to that function, as long as, everything that you accumulate still gets accumulated somewhere. So at the bottom, I'm asking, do we need a canonical way to do that? Is that something anybody else cares about? I'd really like to be able to have our front end generate loops that are sort of theoretically marked as totally parallel, whether or not we currently have anything that's going to use that fact. Okay, communication optimization. So in order to explain communication optimization, I have to start by telling you why we have communication. So, so we've seen already the cofrol a little bit. It's a this would be a parallel program in Chappell, but it's local. It's not doing anything across different machines. This would be a distributed but serial program. It's got 2 on statements in it. And the on statement just means go on to that other machine and then do whatever it is there. And then it's going to wait until that happens and then continue. So this sort of, it's on one machine and it goes over to the next machine and does something, comes back, goes over to the third machine and does something, right? And then here's a distributed and parallel program. You get that by combining the sort of language features. So Chappell's what's called a PGAS language, partitioned global address space. The general idea is to support a shared namespace, but to have all the values definitely kind of have a home so that you know how to access them efficiently. Typical existing PGAS languages are UPC and Fortran 2008 CoRays. So I'm going to skip over this bit, and then I'm going to go through a quick example about what it would look like for a Chappell program in sort of PGAS land and why we might see communication. So we've got a global variable I, so that's going to be on locale 0, because in Chappell everything starts on locale 0. And then it says on locale 1, so now we declare a new variable, we're on locale 1. So we're in this is locale 1 if you haven't figured out the illustration. And then there's a cofrol across all the locales, and it declares a variable k. So now there's a k everywhere. Okay, what if I put some kind of computation in there? What's it going to do? Well, let's think about what happens on locale 3 for this computation. It's going to be 2 times I plus j. Well, what's I? Well, it's going to go and figure out where I lives and read it. So that means the compiler and the runtime will work together to move the value, to copy the values of I and j from wherever they are to locale 3 so that they can participate in this computation. But there's also ways to query locales, but that part about moving the data is where the communication might come from. So communication optimization in Chappell with LLVM, what's that about? So when I described having the runtime move the values, that would be with a get. If it was putting a value somewhere, that would be a put. These are just PGAS terms. So the idea is to use LLVM passes to optimize get and put. And there's this flag I mentioned earlier. Hasn't been working lately, but I fixed it recently, so I'm happy about that. But anyway, here's a little picture. So up here we've got a loop, and it's got a get in it, and the get is to some loop invariant value, right? So then we translate that into a load on a special address space. We're just using the special address space to mark them so that we can untranslate them later. But since it's a load, normal LLVM optimizations like loop invariant code motion, or maybe even global value numbering, can run and hoist the load out of the loop. And then later on, we'll run our sort of lowering pass and take all these address space 100 things and turn them back into gets and puts. So this is the scheme. This slide just explains in words everything I just said. The only new thing that it adds is that as of LLVM 3.3, when we started implementing this, LLVM didn't support address spaces with different sized pointers. Everything had to be the same size. So that meant that we had to make them all 64 bits. So we were using packed wide pointers to work around this issue. But that was not a great strategy from our point of view because it meant that you'd have scalability limits, right? Like maybe you could only go up to 65,000 or so nodes, and maybe you don't care about that. I care about that. And besides that, it also, in some cases, it made the programs run slower than with the C backend because all of this pointer shifting and things would interfere with compiler optimization. So I fixed that recently, and now we're generating LLVM. Sorry, I got it to work at all recently, but when I did, I switched it to use wide pointers instead of packed pointers. So now we're generating LLVM IR with 128-bit pointers, which is probably a little bit weird. I think it's unlikely many other people have been doing this because I found a few bugs that, failed pretty early. Fortunately, there have only been a few bugs, though. And I think these are on the way to getting fixed. Here's a picture of sort of the speed-ups from using this kind of optimization technique. So the big blue bar on the top is showing that this particular benchmark that's a matrix transpose got about 4 times faster. And then the other benchmarks, there's a sort of a class of them that got around, in the 1.5 times faster area, which is pretty good. And generally, it's not making things slower, so I'm pretty happy about that. Because as I said before, we had some cases where it made some things slower and then, can't really use it. Okay, so what are we going to do next? Well, we hope to make LLVM IR generation the default in future versions of Chappell. We're hoping to migrate some of our Chappell-specific optimizations to LLVM IR, because we think it's a really pretty solid representation. We've been, especially in the last couple of releases, improving the IR we're generating. We want to keep doing that. We want to investigate separate compilation. We want to look at just-in-time compilation and building an interpreter. And we'd be pretty excited to work with other groups to have a parallel IR that we can share and share optimizations on. So thanks very much for your attention, discussions, patch reviews, and your related work. If you're doing anything where you're using Clang in some bizarre way, I will randomly go and find people doing that and read your source code and learn from it. So yes, thanks very much.
So we have time for a few questions. There's a mic over here, or raise your hand and I'll come to you and bring the mic to you.
Thanks for the talk. Have you considered, about those extern statements, have you considered running the preprocessor and then building the AST afterwards for parsing C code, instead of building the AST and then kind of trying to figure out afterwards what all the macros mean?
So we do. So the question is whether the macro is being used in C code or in Chappell code. But if we were going to use the preprocessor to sort it out, we'd have to run the preprocessor over the Chappell code. And the preprocessor's not really meant for that. It's for C code.
Yeah, but your the C code is isolated, right? So you got this extern statement,
right?
And then the curly braces, and whatever is in this curly braces is basically a string.
Yeah, I will go back to the example.
Yeah. And then you could just run the C preprocessor on that and basically get rid of all the macros and then just parse that preprocessed string.
Here, right?
Yeah.
If this was using an extern block, instead of require, it would say extern in pound include. And then the macro is used here down in Chappell code.
I see.
Yeah.
That kind of answers the point.
All right.
I had a question. You mentioned a couple places where LLVM didn't support what you needed, such as the address space issue, and there's also the parallel IR issue. Were you ever tempted to make changes to LLVM to support, or did you need to make other changes to LLVM to support Chappell?
Yeah, we have. So I have, you know what, I'm just gonna, I have a slide about this that's in the bonus materials. So here's a list of recent changes that we were making to support some of this effort. But I haven't done a whole lot of changes to LLVM. But these are pretty small.
Okay, let's thank the speaker.